Section 2.6 is about special functions. There are more graphs than just linear graphs, and we're going to look at some of those graphs, some of those functions, what they might look like, and some of their characteristics. We'll start by looking at the step function. It's a function that looks like a step or a stairs, and one of the functions that creates a stepwise function is the greatest integer function. And you use these double brackets, and it means find the greatest integer that's less than or equal to x. So the greatest integer of 7.3 is 7, because it's the biggest integer that's smaller than 7.3. And so negative 1.5, the greatest integer function, is negative 2. So if you were to make a table of values and you plug in any number from negative 3 to negative 2, the greatest integer of that is going to be negative 3. And likewise, you can do that for a bunch of different groups of numbers. From 0 to 1, the greatest integer is going to be 0. Now, if you go and graph that on an xy coordinate plane, this is what your graph looks like, and this is an example of a step function. It looks like steps. Notice there's open circles on the bottom because that circle is filled in on the one up above. And so this picture here is an example of a step function. Here's an example of a situation that will create a step function. It's an auto repair shop, and they charge $60 per hour or any fraction thereof. And we want to draw the graph that represents this. The best way to do it is to make a table of values. So I'm going to plug in some values. We're going to call h the hours or the fraction of hours, and then we'll say the cost, which we'll call c of h, because remember this is a function, so the cost for every hour. So if I put anything from 0 to 1 hour, and notice I'm going to include 1 hour in that list. If I go from 0 to 1 hour, any fraction of that at all is going to cost me $60. But if I go over an hour, and oops, I don't want to include 1 because I've already included it there, and I go anything between 1 and 2 hours, that's going to cost me $120. And I'm going to keep building this. Anything between 2 and 3 hours is going to be $180. I'll do 2 more. So those are kind of the ordered pairs that I'm going to use, but this represents anything between 0 and 1. So because my h, or my hours, is my independent value, I'm going to go down here and just make each one of these 1. So 1, 2, and then here on the side, the cost, and this is money or dollars, so the cost, we're going to go from 60 up by 60, so it makes sense I'm going to make each one of these 60. And then to graph them, I'm going to say from 0 to 1, and we're going to include 1. But we're not going to include 0. So I'm going to use a closed dot there. So that represents the number of hours less than 1, and that's going to cost $60. But then as soon as I go over 1, it jumps to 120. So I leave an open circle, and I continue this pattern. So that's what this situation looks like, and it looks like a step function. Another kind of function is called a constant function, and that's a function that just equals a single number. It doesn't equal any letters at all. And if you go back to regular algebra, you'll remember that we did things like this: y equals a number. So if we say y equals 3, this is the same kind of function that we were dealing with. Here, though, we write it in function notation, f of x equals 3. So when we plug an x in, we get a y value, or a function value, of 3. So if I were to make a table of ordered pairs here, my x and my f of x, when I plug a negative 2 in, I get a 3. When I plug a negative 1, a 3. And this is not something you have to do, but I'm just showing you how it works as a table. So if I were to plot these points, 0, 3, 2, 3, and so on, you end up with a horizontal line. That is a constant function. Our next function is the identity function, and it's a function whose value does not change when you plug it in. So when I plug in an x, I get the exact same f of x. So if I plug a negative 2 in, I get a negative 2. If I plug a 0 in, I get a 0. If I plug anything in, I get exactly what I plugged in. So let's graph those ordered pairs. So here you have an identity function. If you remember back to algebra, this was also called a direct variation. Whenever you plug in, you get out the same value. That's an identity function. Another special function is the absolute value function. It's a function that contains some sort of an absolute value, and it creates an interesting graph that we will look at by plugging in some values. I'm going to use start at -3 for this one, just so you can really get a look at what's happening. If I plug -3 in for an absolute value, I get a +3. And same thing with 2 and 1. Negative values create positives. But if I plug a +1 in, I still get a positive. So look what happens if I graph that. A -3 gives me a +3. A -2, +2. A -1, +1. So it looks like it's going to be a straight line. But then when you start getting to +1, you go back up. So this is a typical absolute value function. It has a V shape to it, and that's what the absolute value bars do to the function, is they create half of the function that goes to the positive x and the half of the function that goes to the negative x. Now this idea of breaking a function as you're graphing it is called a piecewise function. That's a function that can be written using 2 or more expressions. And an absolute value function can be written that way, so it's also called a piecewise function. Now I don't want to leave this absolute value and piecewise function idea until we explore it a little bit more. So here I'm going to have us graph 2 functions. One of them is f of x equals the absolute value of x plus 1, and the other one is g of x equals the absolute value of x minus 2. We're going to examine both of those. We're going to graph them and see what similarities and differences they have. So we're going to build our function by looking at 5 of these ordered pairs. -2 gives me a +2 plus 1. Absolute value of -1 gives me a +1 plus 1 is 2. 0 gives me a 1. So if you plug in those values, those are the f of x values that you get. So we're going to graph that. So here's the f of x function, absolute value of x plus 1. Notice how it's different from the one that we did on the last slide that went right through the origin. This one goes through 0, 1. Well, there's no coincidence that when you add 1 to the end, it goes through that y-intercept. Now to confirm that, let's take a look at the g function. If our hypothesis is to be true, then this one should go through the -2, and let's see if that works by using our 5 points. Absolute value of -2 is 2, minus 2 is 0. So -1 absolute value is 1 minus 2. 0 minus 2, 1 minus 2, and 2 minus 2. Graphing it. So here's the g of x function in green, and yes, our hypothesis remains true that this one goes through -2, and there's the -2 there, while our f of x function went through 1, and that's kind of where the vertex, if you can call it, the apex of the absolute value function goes through. So it turns out that the number that comes after the absolute value controls where it crosses the y-axis. So here's a piecewise function, and we're going to look at how to graph that. My function f of x has 2 different parts to it. It represents x minus 4 if the x values are smaller than 2, and the function represents the number 1 if the x values are greater than 2. So we're going to take that into consideration when we give it some points. We want to pick numbers that are smaller than 2, so I'll start with -1, 0, and 1. And then we want to pick numbers that are equal to 2 and also bigger, so we can kind of get an idea of what happens at that magic spot of 2. So if I plug -1 in, and then I subtract 4, I'm going to get a -5. If I plug 0 in for x, 0 minus 4 is -4. A 1 will give me a -3. But now that I get to 2, because it's different at 2, x is greater than or equal to 2, it's just a 1, which means I'm going to use the number 1 for all 3 of the other points, 2, 1, 3, 1, and 4, 1. And let's see what kind of graph that gives me. Now it breaks right here. So I'm going to graph the first 3, -1, -5, 0, -4, and 1, -3. Now I know that it's going to stop being it's going to stop being this pattern when I get to 2. So it looks like it's going to be a line, but I'm going to put a circle at 2 because I know at 2 it's going to stop doing that because it's a piecewise function. So when I graph the lower half, it's going to look like that. It's linear. But now the upper half is 2, 1. And I'll put a dot there because there's an open circle there, but they'll put a dot there. 3, 1, 4, 1. And it also creates a line, but it's a special kind of linear. It's one of those constant graphs. So it looks like this. So that's an example of a piecewise function. Part of it is a linear that goes down, and part of it is a constant function which goes to the right. Now the last thing we have to do is identify the domain and the range. So my domain is all of the potential x values that can be put in. Well, it looks like all the x values are going to be included on this graph. If I go to the right, it's going to go forever. If I go to the left, it's going to angle down, but it's going to go on forever. So my domain values are all real numbers. I can plug in any number I want for the x's. So my range is the y values, and it looks like my y values are going to go on forever, but there's a hole here at -2. So my y's are going to be smaller than -2. I know that they're going to go below -2. And then there's a hole, because I'm not going to include, -1 doesn't get graphed, 0 doesn't get graphed. There's no y's in there. But then once I get to 1, it just stays at 1 forever. So we can say that or y equals 1. So this is what my range is for this piecewise function, and my domain is all real numbers. So here's a concept summary of what we've just talked about. These 4 new functions we've looked at: the step function, the constant function, absolute value function, and the piecewise function.